Thanks for the introduction. Hello, everyone. I'm Guangming Sheng from the University of Hong Kong. Today, I'm going to introduce HybridFlow, a flexible and efficient RLHF framework. This is a joint work between the University of Hong Kong and ByteDance. In recent years, we have witnessed a revolution in artificial intelligence through the emergence of the large language model, such as the GPT, Cloud, Gemini, Doubao, Qwen, and DeepSeek. This model begins with an pre-training phase on trillions of tokens. After the pre-training, they are fine-tuned using supervised learning on more specific dataset to better follow human instructions. Despite this advancement, the models may still generate biased or even harmful responses, and they often struggle to match the human-level performance on complex tasks. To address this problem, reinforcement learning is introduced in the post-training stage. This process serves two primary purposes. First, aligning LLM with human values. Reinforcement learning from human feedback helps adjust the model's behavior so that it produces safer and more helpful responses. Second, traditional reinforcement learning algorithms, such as the PPO, are applied to improve the model's performance on some reasoning problems like mathematics and code challenges. Reinforcement learning can be modeled as a data flow, where each node represents the computation of a neural network, and each edge represents a data dependency between the neural networks. RL post-training can be decomposed into 3 stages, and we take the PPO algorithm as an example. Here, in the first stage, the actor produced responses from a batch of prompts using autoregressive generation. In the second stage, using the prompts and the generated responses, the reference policy, reward model, actor model, critic model will compute some intermediate states for the PPO algorithm. In the last stage, the actor and the critic are updated using the batch of data produced by previous stages using different loss function. Different IL algorithms follow the 3-stage workflow with different models and different computations involved. In conclusion, the RL post-training can be viewed as a multi-stage, multi-model, and multi-process distributed data flow. Such complex data flow has many unique characteristics. The first characteristic of the RL post-training lies on the heterogeneous model workloads. The actor, critic, reference, and reward model each handles the generation, inference, and training at different stages. They have diverse memory footprints and computation demands, which means that each model requires its own tailored parallelism strategies. So the first requirement of our system is that we should ensure that each model is executed efficiently. The second characteristic is as follows. In every iteration, the actor will perform training and generation, and the actor training is compute-bound, while the generation is memory-bound. So the optimal parallel plan for the 2 stages may be different. Therefore, the actor must reshard its weight between the generation parallel plan and the training parallel plans in every iteration. Although using the optimized parallel strategies for both stages can boost the throughput, the weight resharding incurs significant communication and memory overhead. For instance, training a 70 billion model may require transferring 140 gigabytes of weights per iteration, consuming up to 36% of the iteration time. Therefore, here comes the second requirement. The system must efficiently perform actor model weight resharding. Due to the heterogeneity of different models with distinct parallelism strategies, and the data dependencies between different models will be complicated as a many-to-many multicast. Training data must be resharded across different device meshes. For example, the data from each data parallel group in the source model should be broadcast to all the ranks in the destination model, as shown in the figure. To unify diverse data dependencies across various parallelism strategies, our system must flexibly represent all kinds of data dependencies. The heterogeneity of the model workloads and complex data dependencies becomes even more challenging when combined with diverse placement requirements. Different placement strategies lead to varying computation flows, which in turn affect the training throughput. For example, models assigned to separate devices can execute in parallel when no data dependencies exist, while co-located models or those with interdependent computations must run sequentially in a time-sharing manner. Therefore, our system should support various model placement without changing the code for the algorithm and the core system, so that the user can tune the model placement to achieve the optimal throughput. Building on this characteristic, our goal is to create a flexible and efficient IL post-training framework. We designed the system to flexibly represent various IL post-training data flows, support diverse placement. And also, the system should efficiently execute the multi-stage, multi-model, and multi-process computation workloads. Existing IL post-training system adopt the multi-controller paradigm for data flow implementation. The multi-controller programming model is widely adopted by recent LLM training and generation systems due to its scalability and low dispatch overhead, as discussed by the pathway paper from Google. In this example, a multi-controller IL implementation is shown in the figure. Each model operates through its own dedicated program, with all the workers executing the same code in parallel. However, each worker only possesses a local view of the system and requires distinct point-to-point communication between two models to coordinate the model execution order. Therefore, to implement the IL post-training workflow in the multi-controller architecture, a user must intricately integrate the code for collective communication, computation, and point-to-point data transfer in the program that run at each device. This leads to the deeply nested code of computation and data transfer, making it challenging to develop, maintain, and optimize the frameworks. To address this limitation, we propose HybridFlow, a flexible and efficient IL post-training framework. Our key observation is that utilizing the single controller paradigm on the internal level enables flexible expression of various data dependencies and easy coordination of internal data resharding with minimal overhead. We integrate the multi-controller paradigm within internal communication to enhance computation efficiency. This design effectively decouples inter-node computation and internal data transfer, allowing each model to focus solely on optimizing its local computation without managing the internal communication. And we implement the hybrid programming model using a set of hierarchical APIs. At the internal level, multiple model classes are provided that encapsulate distributed computation of different LLMs into primitive APIs. For example, the update actor here shown in the figure. These APIs can seamlessly support various parallelism strategies from the existing LLM frameworks. This enables efficient distributed computation under a multi-controller paradigm. And we also provide a resource pool class that virtualizes a set of GPU devices. When applying the resource pool instance to a model class, distributed computation of the model will be mapped to the devices. Models utilizing the same resource pool instance are co-located on the same set of GPUs. And models are placed on different sets of GPUs when different resource pools instances are applied in their model classes. And at the internal level, a set of transfer protocols are designed to hide the complexity of data resharding from users, as coordinated by the single controller. We unify this data transfer implementation by associating each operation in the model class with a transfer protocol using the @register decorator. In the example, the update actor operation is registered to a transfer protocol, 3D protocol, as 3D parallelism strategy is used for the actor training. Each transfer protocol consists of a collect function and a distribute function to aggregate output data and distribute input data according to the parallelism strategy of each model. In the 3D protocol, the collect function gathers all the output data or output data filters following the 3D parallel size. Then, the single controller calls the distribute function that registers in the destination model's operation. The data will be correctly distributed based on the 3D parallel size of the destination model. Our single controller is designed to manage the transfer of both data and data futures across the models. And we also support asynchronous data transfer for transferring data futures. In this case, the actual data transfer only occurs between GPUs to avoid any central bottleneck. Our hierarchical APIs enables a streamlined development workflow for various algorithms. User can implement an algorithm as a single process program to run on the single controller. That only involves a sequence of primitive API calls to invoke the distributed computation of the models. As shown in the example, the PPO algorithm can be implemented in just 8 lines of code. And to adapt to safe RLHF, only 5 more lines of code are added on top of the PPO algorithm. To adapt to GRPO, we only need to remove 2 lines of code. That's all about the hybrid controller programming model. And we still left a key point in our system, which is the hybrid engine that supports efficient training and generation of the actual model. In the training and generation frameworks like Maxon LM and VLM, they utilize the same parallelism grouping strategy for the 3D parallelism, where the tensor parallel group and the pipeline parallel groups are formed by assigning consecutive ranks, while the data parallel groups are constructed by selecting ranks at regular intervals. However, this naive design can lead to the communication and memory redundancies during the resharding stage. On some GPUs, for example, the GPU2 as shown in the figure, the training and generation weights doesn't overlap. As a result, training weights are wasted and extra memory is needed for subsequent generation stage. To solve this mismatch, we find that we can simply reorder the grouping logics of the process groups. Specifically, we form the generation tensor parallel group and pipeline parallel groups by selecting ranks at regular intervals, while the data parallel groups are formed by consecutive ranks. By rearranging the generation parallel groups, we can overlap the training and generation model weights on each device. This lets us to reuse weights during the generation and eliminates redundant memory usage in the model resharding. As a result, this optimization cuts the communication overhead by up to 60% and boosts the training throughput. And that's all about the design of HybridFlow. We implement the hybrid controller programming model on top of Ray, and we implement the hybrid engine on top of Maxon LM, PyTorch FSDP, VLM, and SGLang. We deploy HybridFlow on a cluster of 128 100 GPUs. We compare HybridFlow with some recent IL post-training frameworks by comparing the training throughput on different LLM model sizes. We observe that HybridFlow consistently outperforms all baseline methods across every model scales, delivering speedups ranging from 3 times to 12 times. It achieves higher speedup even with larger models. This is mainly because HybridFlow can efficiently execute generation, inference, and training in all IL stages by sharding the models with different parallelism strategies to fit various computation workloads. HybridFlow reduced the transition time by 55% on average and by up to 89% with 17 billion models. HybridFlow also maintains stable transition overhead across various cluster scales. This is because HybridFlow enables zero memory redundancy during the transition and requires only one all-gather operation on a relatively small communication group. HybridFlow supports various placement strategies, and we conclude 3 main insights for the model placement and the GPU allocation in the IL training. First, collocating all the models is the most effective on most cases. Second, when scaling up to larger scale clusters, distributing the actual and critic model of different devices for parallel execution in the training and preparation stages will help achieve even higher throughput. Third, as the actual model often render the majority of the workload in each IL iteration, allocating more GPUs to the actual model can reduce the generation latency. To conclude, we believe that our hybrid controller programming model in the HybridFlow is the key to represent the complex IL post-training data flow. The single controller can flexibly express data dependencies of different IL algorithms and support various model placements. The multi-controller can efficiently execute LM training, inference, and generation. 3D Hybrid Engine accelerates the training process by introducing the zero redundancy resharding. We have open source HybridFlow on GitHub under the repository named VERL, which has recently gained over 6,000 stars. HybridFlow has been widely adopted by tech companies such as ByteDance, Alibaba, and Amazon, as well as by the broad academic community. I encourage you to try HybridFlow for IL post-training, and we welcome your contribution to further enhance and evolve the project. Thank you. I'm happy to take any questions.